In March of 2026, astronomers detected the brightest fast radio burst ever recorded. A radio signal from a galaxy 130 million light-years away arrived at Earth and briefly overpowered every other radio source in its corner of the universe. The burst lasted 1/5 of a second. In that time, it sent more energy than our sun will produce in weeks. Yet when researchers searched 6 years of archived observations, they found no trace of a second burst from the same location. This is the central mystery. Most fast radio bursts repeat. This one did not. Fast radio bursts, or FRBs, are among the most elusive phenomena in astronomy. These transient radio signals arrive from distant galaxies and disappear almost instantly. Astronomers have known about them for only 2 decades. The first confirmed detection came in 2007. Since then, the field has grown exponentially. Radio telescopes across the globe now dedicate observing time to searching for these signals. Each discovery is brief, intense, and utterly strange. An FRB's entire lifetime can be shorter than a lightning strike. Yet the energy released rivals that of an exploding star. Astronomers long struggled to locate FRBs at all. A burst would arrive, fade, and leave no clear indication of where in the universe it originated. This changed in 2018 with the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. CHIME is not a traditional telescope. It is an array of dipole antennas, each one resembling a modified television antenna. The array spans the area of a football field. It observes the sky not by moving or pointing, but by analyzing incoming signals. CHIME changed the FRB field overnight. It discovered more FRBs in its first year of operation than had been detected in the previous decade combined. But CHIME alone could not precisely locate these bursts. A burst would arrive and vanish before researchers could determine its origin. This is where CHIME Outrigger enters the story. Outrigger is an expansion of the original CHIME array, consisting of smaller instruments deployed in British Columbia, Northern California, and West Virginia. Together, they employ a technique called Very Long Baseline Interferometry, or VLBI. VLBI works by combining signals from multiple dishes, separated by thousands of kilometers. The separation creates baseline distances that allow researchers to locate radio sources with precision comparable to optical telescopes. For RBFLOAT, this technique achieved real-time localization, pinpointing the burst coordinates before follow-up observations could even begin. An FRB named RBFLOAT arrived on March 16, 2025. Researchers announced the discovery on March 15, 2026. The designation RBFLOAT stands for Radio Brightest Flash of All Time. The signal originated in a spiral galaxy called NGC 4141, located in the constellation Ursa Major. The localization technique pinpointed the source to a region spanning just 45 light-years across. This precision was extraordinary. RBFLOAT outshone every other radio source in NGC 4141. The burst lasted 0.2 seconds. In that fraction of a second, it briefly became the brightest radio object in its entire home galaxy. Imagine a signal so intense that it dominates an entire galaxy's radio output. Then it was gone. This is what makes FRBs so difficult to study. They arrive without warning. They vanish before most instruments can even respond. Conventional observations of FRBs are like trying to photograph lightning. Successful observations happen by chance, not by plan. RBFLOAT's brightness gave researchers an unprecedented advantage. It was loud, it was unmistakable, and it allowed follow-up observations that most FRBs do not permit. James Webb Space Telescope pointed at the location CHIME identified. JWST found something unexpected, a faint infrared signal at the burst's exact coordinates. This signal could originate from a red giant star. It could be light bouncing off dust, a phenomenon astronomers call a light echo. Or it could come from something else entirely. The nature of this infrared source remains unidentified. Here's where RBFLOAT breaks the pattern. Most extensively studied FRBs repeat. Researchers observe them multiple times, sometimes over years. This behavior has led theorists to propose a persistent source. A leading hypothesis involves magnetars, neutron stars with extraordinarily powerful magnetic fields. Magnetars occasionally flare, sending outbursts that propagate across space as radio signals. A magnetar produces repeating FRBs because the star itself is stable and long-lived. Astronomers expected most FRBs to follow this model. RBFLOAT does not fit. Researchers examined 6 years of archival data from CHIME and related instruments. They found no additional burst from RBFLOAT's location. This single event, this 0.2-second flash, may be all astronomers will ever observe from that source. This discovery coincides with a broader surge in FRB detections and a revision of theoretical expectations. In January 2026, the FAST telescope, located in China, discovered a repeating FRB within a binary star system. Two stars orbited each other, and one of them produced repeating radio bursts. This environment was unexpected. Magnetars in binary systems are rare, yet here was one emitting FRBs. In May 2026, CHIME reported the discovery of 30 new repeating FRB sources. These additions brought the catalogue of known repeating FRBs to 80. The rate of discovery has accelerated dramatically. The population of repeating FRBs has expanded far beyond what theorists predicted 5 years ago. Yet RBFLOAT stands apart. It is the brightest FRB ever detected. It is non-repeating, and it resides in an ordinary spiral galaxy, not in an exotic stellar environment or near a binary companion. If RBFLOAT originated from a magnetar, why does it not repeat? If it came from something else, what was that source? Alternatives include neutron star mergers, collapsing massive stars, or phenomena not yet theorized. And why did RBFLOAT shine so brightly for such a brief moment? Why did NGC 4141, a relatively ordinary galaxy, produce the most brilliant FRB in the observed universe? These questions drive the field forward. Astronomers will continue to search for more non-repeating FRBs like RBFLOAT. They will train infrared telescopes on archival locations of known bursts. They will refine VLBI techniques to localize future FRBs with even greater precision. They will search for patterns in the properties of repeating versus non-repeating bursts. RBFLOAT did not answer what causes fast radio bursts. It only posed the question more sharply. Why would the brightest FRB ever detected come from a source that does not repeat? What principle of physics could explain this contradiction? These questions will guide the field forward as astronomers work to understand one of the universe's most enduring mysteries.